All right, so here we are in AP Calculus. This is a Calculus 30L concept. This will be on your advanced placement exam. So this is part of, it's beyond Calculus 30. We are exploring here again the fundamental theorem of calculus, and this is where we would have left off. Probably you would have left off in your Calculus 30 course, is learning about integrals, right? And learning about indefinite and definite integrals. So that's where we ended off, and I'm just going to start this lesson here today. And we're going to learn, basically, we're going to explore the definition of the fundamental theorem of calculus. We're going to explore that a bit more today because, yeah, there's certain parts of that that I kind of skipped over a little bit in our basic introductory course. So the fundamental theorem of calculus, what did we learn about that? Okay, well, the fundamental theorem of calculus is where we introduced integrals. And of course, an integral comes from the antiderivative concept. So we studied in Calculus 30, basic introductory calculus was mostly differential calculus. And so we talked about derivatives of things. Awesome, derivatives. Instantaneous rates of change, great. We also found out, though, that sort of the opposite operation for taking a derivative is taking the antiderivative. And right here, you'll notice here, when we have a function of, let's say, f of x is our function, right? Okay, so f, the function is continuous on AB. F of x is the function. The antiderivative is capital F of x. You remember that? So we take the antiderivative and we get capital F of x. We then explained that the antiderivative can also be viewed as an integral, and we introduced this long s symbol here. Okay, the elongated s with also a little differential of the variable here at the end. And so we said that, when you take the antiderivative, it can be interpreted as something called an integral. And the integral, so if this is the function here, let's say, right here, a function, the integral, let's say from a to b, can be interpreted as the area under the curve. Okay, so we've got f of x, and this area is sort of like capital F of x, or the integral from a to b of f of x dx. And so this is called a definite integral when we have limits of integration. Okay? And really, if I skip down here, you see this, in most textbooks you'll see that what we learned about as a definite integral is actually the fundamental theorem of calculus part 2. Okay? So when we were evaluating. So part 1 is explaining this. And you would have heard this, so you'll understand this, but we're going to take it a little bit deeper today. So if you take a function and you differentiate, you can find the instantaneous rate of change. But if you take a function and you take the antiderivative, that's like finding the area under a curve. But here's the important part. If you take the derivative of a function and then you take the antiderivative, you get the function back. In other words, differentiation and integration are sort of like opposite operations. They undo each other. That's very important. And that was the first thing that we really learned about an integral, a derivative integral. So it also can be stated that any function, okay, if you're just given a function, f of x, let's say, it has an integral and it has a derivative. But also that function is the derivative for another function. Or this function is the integral of another function. So we have like g of x, f of x, h of x, okay? And any function is the derivative of another function, and any function is also the integral of another function. So that's really important. Now, this notation is maybe a bit strange. We didn't really delve into this, and this is what I want to focus on today. Let me just zoom in a bit here. If you take the derivative of an antiderivative, that's what this is showing, then it looks like this. The derivative of, well, let's just write that as an integral. But what's strange about this is the integral and the limits of integration here are different. Notice this is a constant. This is a value, a variable x. This is a separate variable t, okay? This is where it gets a little bit confusing, and that's what we're going to focus on here today in our lesson. But the bottom line is, the derivative of an antiderivative over here is the original function, okay? The derivative of an antiderivative, you get the original function back. So let's explore this middle part here. We're going to explore this middle part here today. All right. So the importance of this statement that we just learned, it cannot be overstated. It is very, very powerful. And of course, as I just mentioned, I'll just read what they have in the textbook. And if you're following along in the textbook here, we're in the Finney textbook, the orange and blue one here, Calculus, Graphical, Numerical, Algebraic, AP edition. And we're on about page 294 here. So if you have that textbook, you can open up to about page 294. But what this is saying, okay, what this is saying is that, as I mentioned, every continuous function f is the derivative of some other function, namely the derivative of this, which is the integral. It's the derivative of the integral. Okay. Every continuous function also has an antiderivative. Okay. It also says that the process of integration and differentiation are inverses. Remember I said opposite operations. Very important. Okay. So yeah, that's why it's called the basic fundamental theorem of calculus. Okay. So this is the one we focused on in Calc 30. A definite integral where we have limits of integration. And in order to evaluate this, right, we took the antiderivative of f of x. So remember, antiderivative and integral go together. And we evaluated that antiderivative at b. And then we subtracted the evaluation of the antiderivative at a. So this is what we focused on in Calc 30. Okay. But this here now, we're going to explore further part 1. Okay. So let me first of all explain what's going on here with, because this is the tricky part. Okay. We've got an x here and we've got a t here and here. That's the tricky part. Okay. The derivative of an integral or the derivative of an antiderivative. Opposite operations. Okay. So I like to explain this by doing a little bit of an example, okay? So let's say that we're going to focus on this part here, just the integral part, okay? We're going to leave the derivative part for later. I'm going to focus on the integral part, okay? Now, if I was to take the integral of this, and of course this is a definite integral, we know about this, right? So we did in Calc 30. So what we do is we take the antiderivative of cos, which is what? Sine or negative sine? Okay, so the antiderivative of cos is sine because the derivative of sine is positive cos. So we've got sine of what? Well, we've got sine of t evaluated from negative pi over 2 to pi. Okay, and we would be able to figure this out, and it would look something like this: sine of pi, sine of pi, right? Minus sine of negative pi over 2. So the limits of integration there. And that's what it looked like. And we could, simplify that and we get an answer. Okay. Now I'm not going to focus on this too much, what the actual answer is. Well, I guess let's do it. Let's find the actual answer there. Okay. So sine of pi is what? You remember sine of pi? Here's the point here on the unit circle. That's negative 1, 0. Sine is the second one. So that's 0. Negative pi over 2, that's this way. That's going to be this point on the unit circle. So what is that? That's 0, negative 1. So that's a negative 1, right? Am I doing this right, you think? So that's 1. Okay. Now, how else can we look at this? If you remember from Calc 30, negative pi over 2 is over here. Pi is over here. And so we've got the, this is what the graph kind of looks like. Okay, these two sections would cancel out, and we would have sort of this section here would be, I guess, our result here. Okay. All right. So now here's the situation where we have an x. Okay, we have a constant down here, and we have an x. Okay. So again, I'm going to get to the derivative in a second here. Here's the derivative part. Okay. But again, let's focus on the integral first. So this would look like this. I would have sine of t evaluated from negative pi over 2 to x. Okay, so if I have an x here, how is that going to change things? Well, that's going to be sine of x minus sine of negative pi over 2. Okay, you see that? And I notice that this is a function of x, and this is a constant. That's a constant. So now let's bring in the derivative part. So let's say we are going to go ahead and do this whole question. I'm going to take the derivative of this. Okay? The derivative of this. And notice the key is that this is a variable, not an actual number. And so what happens is when I take the derivative of sine of x, I get cosine of x. When I take the derivative of this, it's a constant, right? That's a constant. And so this is 0. So what do I get? I get cos of x. Cos of x. Now the key is that this is a constant, and it comes from this part of the definite integral. Okay, so this helps me, and hopefully it'll help you, make sense of the fact that this constant here can actually be any constant. Any constant. It can be negative pi over 2, it can be negative pi, it can be positive pi, it can be anything. Because when we take the derivative of the integral, it's sort of like these two things go away, right? Those two things go away. And I'm taking a look at whatever this is right here. It's almost like they undo each other. But when you have a variable here, this variable goes in there. That's how that works out. It works out every time. Okay? So if we have just a plain old x, not x squared or 3x or x over 2 or anything like that, that's a little bit different. We're going to talk about that soon. But when you have this situation, and I'll go back to this right here, d dx of this integral is whatever this function is right here with that variable put in there. Okay? It's sort of one undoes the other. And that's why it doesn't matter what constant this is. Oh, that should be a pi. It doesn't matter what constant this is. Okay? Now, here's some examples here to follow that up. And this is what you're going to be seeing in your textbook and on your AP exam. Okay? When you have the derivative of an integral, you know that those are going to kind of balance, they're going to cancel each other out. And this should be a constant down here, which it is. And if this is a variable x, then simply this variable goes in here. If we take the integral of this, then take the derivative of this, we get the same thing back. And so, down here, if you have the derivative of an integral, as long as the upper limit is x, you put that variable in there, and this is your answer. Okay? One undoes the other. Same thing. Whatever the function is, no problem. As long as this one's going to cancel off this one, and this is a constant, I put this variable in for my variable for the integrand there. Okay? All right. All right, so I'll show you just how easy this is here. Now, if I want to find y prime, okay, take the derivative, okay, so find y prime. So I'm taking the derivative with respect to x here, the derivative of both sides. Well, what does that do? This gets rid of the integral. And I have a simple x right up here, so that goes in for the variable in my integrand right here. And so the answer to this, if you take the derivative of y, the derivative of an integral gets the original integrand back, except with this variable. So this is simply x cubed minus, x, all to the power of 5. That 5's outside the brackets. And that's it. That's it. Okay? Over here, if I take the derivative, d dx, okay, or dy over dx, I take the derivative of both sides. Well, the derivative and the integral kind of cancel each other out. I have a constant here, that's good. And I have a variable here. So guess what? The derivative of this integral is tan cubed of x. Tan cubed of x. Okay? Question is, do we have to worry about the plus c? Well, again, if you're taking the integral here of this, which we didn't actually do, you don't have to do that, but you would get a plus c inside here. And then when you take the derivative of that constant, it's 0, so it's gone. So you don't have to do a plus c at the end. No, it'll just be plus 0. Okay? All right, so that's just the first level of exploration of the fundamental theorem of calculus part 1. Now, what we're going to do now is find out what happens if we don't have just an x here, okay? What happens if we have like an x squared or a 2x or a 3x cubed or something like that? So this is the type of question we're going to look at now. And you know what? It's not that difficult at all. As a matter of fact, what we have to think about is this: chain rule. That's all we have to do. We have to think about chain rule. So notice the upper limit of integration is not x, but it's x squared now. So it's not a straight x. The derivative of x is 1. The derivative of x squared is not 1. So we have to take into consideration what would happen when we integrate and then take the derivative. If we're talking about a function of something other than x, when we take the derivative, we would have to do the chain rule. Okay? So this makes y technically a composite function, and what we're going to do is we're going to take this function, whatever it is, and we're going to let it equal to u. So a little bit of a u substitution here, okay? Okay? So if we took the derivative of y, so here's y. If we took the derivative of y, we would, with respect to x, we would have to take the derivative of y with respect to u and then do chain rule. Derivative of u with respect to x. So simply, this is not hard, but simply what this looks like is this. If you see this as just a u, okay, the derivative of u is 1. And so this, let's get messy. This cancels off with, sorry, I just realized, I see that chat come in. I was paused, right? Sorry, should be back to normal here now. So the derivative cancels off the integral. And we just have u up here. So this cos of t becomes cos of u. But because u is a more complicated function, we have to multiply by the derivative of u. We have to do the chain rule. And so simply this is what you end up getting. Okay, so just to go over this part again here, if we have a function that is not just x, okay, if it's something like x squared, let's do a little bit of a u substitution. And now that we have just this u here, then the derivative of the integral with respect to u right here is just cos of u. See, we get this back. The u goes there. But because u is a substitution of a different function, when we differentiate, okay, when we differentiate the u part, we have to actually do chain rule. So it's pretty easy. The x squared goes in for the variable, and then you have to multiply by the derivative of x squared. Okay, that's it. So you have to remember the chain rule. Remember the chain rule. If this right here, if the upper limit of integration is not just x. So let's do a couple examples here. Okay, let's do a couple examples here. So again, we're going to find derivative, right? Find dy dx, okay, for y equals this integral. So dy dx equals d dx of this integral 0 to x squared e to the t squared dt. Now again, a couple things you want to remember is that this integral, if it's dt, you'll have a t, or this variable, inside in the integrand. Okay, this is our this x squared, okay, the upper limit. Here's a constant, that's good. This is the upper limit and it's an actual function of x. That's great. This and this need to match, x, dx, and x. So if that's the case, this derivative will undo that integral. And what we have is we have e to the x squared squared. So I put x squared in for t. But because that's not just a plain old x, you got to remember, you got to multiply by the derivative of x squared. Okay? So times the derivative of x squared is 2x. All right? So the derivative of the integral cancel each other out, but because it's not just an x, you got to multiply by the derivative of the u. So what does this become? This becomes 2x e to the, and if you have a power raised to a power, you multiply. So it looks like this should be e to the power of x to the 4th. Okay, so for number 10 here, for this one here, now if you want to pause the video here, if you're watching the video, if you want to give this a try right now, I encourage you to do that. Once you give that a try here, press play again and I'll show you the answer. All right, so if we're taking d dx here for number 10 of both sides, we know that d dx of an integral, especially when it has a limit of integration that has to do with x, these are going to cancel each other out. And what we need to do here, sorry. So yeah, we put 5x in for u, wherever you see u. And then we need to multiply by the derivative of 5x, right? Chain rule. So what do we end up with here? The derivative dy dx is actually square root of 1 plus, now this is 5x squared over 5x. You just plug that thing right in there. Times, what's the derivative of 5x? Well, that's 5. Okay, so we should simplify that, shouldn't we? So let's go square root of 1 plus 25x squared over x, because the 5 and the 5 cancel out. Okay, so let's double check that. All right, so that is indeed the correct answer for number 9 and 10. So yeah, fundamental theorem of calculus. It's technically part 1. The derivative of an integral counteracts, it cancels each other out. You put in the upper limit of integration. If it's a variable, you put that into the integrand. If it's a variable other than just an x, if it's a 5x or x squared, then you also have to multiply by the derivative to do the chain rule for the differentiation. Now, one thing that's going to be a little tricky is this one. Do you notice what's different about this type of question? Very similar. Do you notice what's very different? What's different is we have the constant on top as the upper limit of integration and the variable on the bottom. Now, if we were to evaluate this integral, okay, and maybe I'll just do this quickly on the side and show you. Okay, I'm not going to bother doing this on the side here right now, but what you would have, watch this, you would have the integral, okay, whatever the integral is here, and you would have this evaluated from x to 7. And the evaluation of that would be the integral with 7 in it minus the integral with the x in it, right? And so what is this? And when you take the derivative of this now, so if we were to take the derivative of everything here, well, you're taking the derivative of this, and guess what? Your constant is here, right? That's the integral, which is just this little squiggle, right? Evaluated at 7, so that's a constant. And this is your variable function, okay? So what's different? Well, what's different is this minus sign, okay? Okay, so now I'm going to get rid of all this. There it goes. Going to be gone, okay? And, oh, look at what I just did there. Okay. I just erased, what did I have? Oh, I had a little, I had a little white box covering the answer. Ooh, I'm pretty smart. I'm so smart I outsmarted myself. All right. So think about it this way, and you can also think about the properties of integrals if you remember from Calc 30. Okay. So this, if you put a negative in front of this integral changes to this. Okay. It changes to this. So that's the property that we're going to use here. Okay, so you have to have this on top, for all this to work. And if you don't have the variable as the upper limit of integration, just take the negative of the integral, and that in effect flips the limits of integration around. All right, so now that we know this, it's pretty easy, right? The d dx here of both sides, okay, of everything here, is going to be equal to this, negative square root of 2, what? X to the 4th plus x plus 1. And because this is just an x, it's not an x squared, a 5x, a third x, or an x squared plus 1, or a cos x, or anything crazy like that. It's just an x. I multiply by the derivative of the x, right? dx, dx, right? Whatever, that's just 1, right? So I don't really need to do the chain rule. And here's your answer. And let's see if that is the answer. I think, oh, look at that. Is there a negative in front there? Should be a negative in front there. Okay. There we go. Oh yeah, I didn't even +1. Okay. Okay, any questions about that? Online class, any questions about that one? All right, there is your answer. So that's the lesson on the fundamental theorem of calculus part, well, technically part 1. It's the second run at it, right? This is a bit of a reprisal for the fundamental theorem of calculus if you did it in the same order that I did it with my classes. So again, just a quick overview of where we came from here. Okay, the derivative of an integral, they cancel each other out. The only tricky part is what happens when you have a variable there as a limit of integration. Well, it's not that hard actually at all, is it? Okay, so that's what we were talking about today, and of course you need to know how to do these examples that we've ran through. Okay, fundamental theorem of calculus, part 1 and part 2. Okay, now I'm going to show you in the textbook here. If you want to do some practice, my class will have to be doing some practice here. So take a look at these questions right here. You have the answers right there. Some of them we've done already, but get some practice with those right here. And that rounds out our lesson for today.